So the first thing I want to quickly talk about is why. So why would we be interested in solving an inequality instead of solving an equation? And honestly, equations get all of the press when it comes to algebra class. Inequalities get a short shrift. It's a topic that sometimes gets touched on really quickly and then moved past really quickly. But we need to sit with it for a couple weeks, maybe 3 weeks or so, to really wrap our heads around what they can do for us. So I kind of want to start with the example that's at the bottom of this list here, example 3.2.13. So in this example, this is a story problem. And so we're going to sort of together do the work of unpacking the mathematics out of the story problem. But as you might expect, being that it's placed where it is in the text, that the solution of this will require us to wrestle with an inequality. So here's the idea. Rhonda is in a class in which tests are taken, and the average of those test scores becomes a part of your grade. So she's not in our class. We don't do points and averages and percentages and that stuff in our grades. We have a totally different grading system, but this is probably the one you're more used to. And so the question is, if she got a 78 on her first test and a 54 on her second test, and she wants to end up in the class with a grade of 70 or better, so she wants to get that C- or better, then the question here is not what score does she need, but the question is rather, what's the lowest score that she would need? Because she could always get better, right, and still meet this criterion. But if she wants at least a 70 for her average, then we know that the answer to this question is she's going to need to at least do however well on the next exam. Right? And so where we put in the word at least gives us a clue to the fact that this is not a problem where we're going to come out with a single number as an answer. It's a problem where we're going to come out with a whole range of numbers that are the solution to this problem. And so that's why this becomes an inequality. Let's quickly unpack the arithmetic out of this story problem so that we can get to a place where we can use the strategies that we know. So we know that her first two tests were 78% and 54%. So that much we know, 78, 54. And her third test, that's the test whose score we don't know. And so how should we represent that quantity, given that it's a number whose value is not known right now? What should we call it?
X.
Yeah, let's just call it X, right? It stands for a number. It stands for a number whose value we don't know. We cannot know because this test hasn't happened yet, right? It's a quantity that exists only in the future. So we're going to call it X, and we're going to make that her third exam score. Okay. And the other bit of information that we have here is that she wants her average for this class to be at least 70. So the first thing I want to do is I want to put 70 over here on the right-hand side of the screen. And then I need to figure out how to translate these other bits of red knowledge here into algebraic operations for us to do something with. So the first question I have is, if I have three numbers, how do I compute the average of those three numbers? What's the process there? Basic statistics dictates that the average is the number which we would get if we combine the total of everything and distributed it into equal parts, right? So that means the average of these three numbers is their sum, so add the three numbers up, and then divide the result by 3. So there's the average of all three tests. Average of 3 tests. And I know that 70 is the course average that I want, but really I don't want just 70. I would be just as happy with a 71, or a 72, or a 73.5, or an 82, or a 96.4, or a 98.9, or 105.6. I would be happy with any number as long as it's at least 70. So how do we represent that at least part of this formulation in a symbol? What symbol do I want to use here? Greater than or equal to, right. So when we say at least 70, we're allowing for the possibility that this number could be equal to 70, or it could be greater than 70. And so we'll use this symbol which we also read as greater than or equal to. So that's what makes this an inequality problem, is I don't need my average to be 70, I just need it to be 70 or more, right? Greater than or equal to. And so it turns it into an inequality problem. And so because my problem is an inequality, its solution will also be an inequality, right? It's going to tell me in order to get a 70 or better as my course average, I'm just going to make up a number, I need an 81. Or I need something more than 81. So if I get more than 81, then my average will be more than 70, and that's okay, according to the original problem. So inequality problems have inequality solutions. And that's the first thing that makes them different from when we solve equations. One of the more powerful tools that I believe exists in thinking about inequalities are the ways that we can visualize, draw a picture of what's actually happening here. And the kinds of pictures that we often use are these number line pictures. I have a pretty stubborn visual learning preference myself. I really find that having a picture is worth more than 1,000 words for me. And so one of the ways that we might think about what this inequality that we've written down here is telling us is that there's a number, 70, on the real number line. I just realized I wrote down the symbol for the real number line without telling you that's what it is. Sorry, it's a reflex. I'm also teaching a math majors course called Real Analysis, and that's what we do every single day. Right, so this just means the real number line. Maybe we'll forget that's there for a minute. And just think of this as the number line. And there's a number 70 on that number line. Let's put it right here, for example. And what this inequality is telling us is that the course average, the value of this expression, 78 plus 54 plus x all over 3, the value of that average needs to be up here somewhere. Right? So this quantity must be somewhere in this interval, which goes all the way down to 70, but it can go up as high as you like. It could be 80, it could be 100, it could be 600, it could be 6 billion, right? I mean, there's nothing in the inequality that tells me it can't be that large. So I'm not describing a number, I'm describing a whole range of numbers, or what we call an interval of numbers. And I can describe that interval in this picture. Often, though, what we'll do in this picture is we'll be real specific about whether the number 70 is actually included or not, because the picture is a little bit ambiguous. It's hard for me to tell from the picture whether 70 actually belongs to this shaded region or whether it doesn't. According to this inequality, should 70 belong or should 70 not belong? It should, because we're allowing for both greater than, which accounts for everything to the right of 70, but we're also allowing for the equal to, right, 70. And therefore, 70 actually belongs as part of this interval. And what we usually do to represent that is we'll put a solid circle right there on 70 to just reinforce the point. So the interval of real numbers that I'm talking about begins with and includes the number 70, and then also includes everything which is greater than 70. So that's kind of one picture of how I can write that. There's one other way that I can communicate about this, not using a picture, but using a different way of writing, a different way to communicate. And the other picture is what's called interval notation. And this seems to be the place that trips people up the most, because it turns out not even really being about mathematics as much as it is about a way of communicating, a way of writing down this set of numbers with a minimal set of information, basically finding a way of using notation to convey the same information that this picture does. And the way it works is it asks us, first of all, how far to the left on the number line does this interval go? And then how far to the right on this number line does this interval go? So how would you answer, first of all, how far to the left this interval goes on the number line? Well, 70. Right? That's the left-hand endpoint. So I'll write the number 70. How far to the right on the number line does this interval go? Infinitely far. It goes all the way out. There is no upper limit to this interval on the right-hand side. So we'll use infinity, or if we want to be really specific, positive infinity, the horizon at the right end of the number line. We'll call it positive infinity. We'll use that as our right-hand endpoint for this interval. We'll put a comma in between those two things. Right? So this is going to tell me that I'm looking at an interval of real numbers that starts at 70 and it doesn't end toward the right side. Right? It goes all the way out to the end of the real number line, which doesn't exist. Okay, that's not the part that usually trips people up. It's the part that comes next. Because we also want to introduce some notation that tells me over here whether or not I'm going to include the number 70 or whether or not I'm going to include the concept of infinity as a part of my set. 70 is the interesting one to talk about. So we decided that we wanted 70 to satisfy this inequality. So it needs to be included in my interval. So I just want a piece of notation here that tells me that reinforces this closed circle that we drew at the number 70. Does anyone know what the piece of notation is that we use next to the 70 to indicate that it's included in this interval? Yeah, yeah, it's either a bracket, a square bracket, or it's a parentheses. Right? So those are our two options. Right? One of these means that we're going to include the number that's next to it. The other means that we're going to not include the number that's next to it. Just based on visual, which one do you think indicates inclusion, and which one indicates we get right up against it but we don't include it? Which is the inclusive one? So the parentheses, to me, the visual of a parentheses is it's rounded on the end, and so we kind of get real close to the number 70, but we don't quite get there. Whereas the square bracket, it goes right up to the number 70 and includes it. So to me, there's a little bit of a visual there that helps to reinforce it. So we do actually want the square parenthesis on the 70. So these mean include. It means that the number next to it actually belongs. That's the same thing that this closed circle here means, right? So anytime there's a closed circle in my interval, when I sketch it on the number line, those closed circles are going to turn into square brackets in our interval notation. Round brackets then, round parentheses, do not include. So let me ask you about infinity. Is infinity a number which belongs to this interval? If I were Rhonda, and I did so well on that third exam that my course average was infinity, then would that be okay for this inequality? Yes or no? Yeah. Difference of opinion. So why might it not be okay? Because infinity is not a number. Right. Right. So that's actually, we can fall back on that as a crutch. Anytime we're writing down an interval that has an infinity at one end, infinity on the positive or the negative side, because infinity is not a number, we're never going to include it as part of our intervals. So infinity will always get a round bracket next to it, never a square bracket, at least not for our course. In fact, even in most courses in the math major, we never include infinity as part of our arithmetic, because infinity is not a number. We can't do arithmetic with infinity in any way that makes sense, which is compatible with the arithmetic of the rest of the real numbers that we know. So infinity will always get the round bracket. But then for finite endpoints like 70, we have to separately make the decision, do we include it so it gets the square bracket, a filled-in circle, usually correlates to a less than or equal to or greater than or equal to symbol, or do we not include it, which would be a round bracket, a hollow circle, and usually a greater than or less than sign without the equal next to it. So those three things tend to occur together.